this on? All right, thank you all for coming. We're here to talk about the Netflix front door and what it takes to run it. We're going to give a couple examples, both in terms of slides, and Ben's going to do a demo of a range of these things. So about us, both Ben and I, we operate the edge engineering team, which basically is the front door. What it means is if there's no one there to answer the front door, then nobody gets to stream Netflix, and it's our job to make sure someone's always there to answer it. So if you want to follow us on Twitter, that's our stuff. How this really translates is Netflix is responsible for about a third of the internet traffic in North America, and various other spots throughout the world where a massive amount of traffic. It's incumbent on us to make sure that we can sustain these levels, both in terms of the downstream traffic, the 33 or 34.5%, but also in terms of upstream, which is less commonly reported on as a metric. So we're responsible for about 6.5% of the upstream traffic as well. So more specifically, what do we do as an edge engineering team? First, and this is probably our prime responsibility, is to broker data between devices and servers. And that comes in different forms, both in terms of writes, things like adding things to your queue or rating titles, but also in terms of reads, creating the discovery experience as you're browsing around, looking for titles to watch. We're also responsible for the playback flow. So when you actually press the play button, it triggers a series of events that will start the stream of the video. So that also falls on this team. Resiliency comes in a couple different forms, and that is hugely important for us. It comes both in the form of Netflix, the edge engineering team needs to be responsible for ensuring that we don't fall over. But because we're at the front door, right at the edge before we deliver to clients, we're also responsible for protecting the customer from a range of other failures that could happen underneath us, and we'll talk about that throughout this presentation and demo. Scaling the systems, that comes in different forms as well, both in terms of the breadth of things that we need to deal with. We're on 1,000 different device types, dealing with the cardinality of that and scaling horizontally, as well as throughput and scaling the systems to handle many regions, more users, things like that. Because we're in between all the servers and all the service teams and all the devices, we need to be keen on velocity. We need to make sure that we as a team can deliver our responsibilities as quickly as possible. So we spend a lot of time and energy on things like continuous delivery and making sure that we can get code into production daily, multiple times a day. And then we also provide real-time health metrics. Basically, we're the umbrella on top of the rest of the service organization, so we can actually have a purview, a unique view into the health of the system. And so it's incumbent on us to share that. So today, we're going to talk primarily about resiliency and scaling the systems. If you want to learn more about insights, someone on the team, Sharma Padilla, is speaking on Friday about scheduling within the Mesos environment. So you can learn about that at 9 o'clock on Friday. So a high-level view of our architecture is basically 1,000 different device types. They have to call into our service. They're going to cross the HTTP border and hit first the ELBs, which is basically reconciling the DNS. Then they're going to call into Zuul, and we'll talk a bunch about Zuul today. Zuul then handles the routing to origin servers. In this case, origin servers, I'm representing that as APIs. There are others, I'll show you in a second. But that routing to an origin server is basically controlling where the traffic's going to flow so that an origin server can do the processing and actually handle whatever the request is, get the data, do the right event, whatever it might be. And then each of those origin servers are going to call out to a breadth of different dependent services that are actually doing the computations or handling the data. Other examples of origin servers include playback, website logging. Zuul fronts all of those. But for today, we're really going to focus in on the interaction between Zuul and the API backend. So, routing traffic. Zuul, again, this is a fundamental part of the system. It truly is our front door. It does a wide range of things for us, including things like multi-region resiliency, load shedding, insights, squeeze testing. It's hugely helpful in basically controlling the flow of traffic, and having it separated out from the origin gives us great flexibility in how we can handle that without compromising the computations that we need to do. So going back to this diagram, a request basically routes as follows. It goes from a device, hits an ELB. That ELB is going to send the traffic onto a corresponding cluster of Zuul. Zuul's going to send it on to an origin server, in this case the API, and then the API is going to fetch or process data with a dependent service or multiple dependent services. And in fact, the ratio of dependent services for an incoming request from a device is somewhere around 7 or 8 to 1. So generally, one request coming in is calling out and processing with many different dependent services. So that's the happy path for Zuul. That's the typical path. There are other ways in which we're going to control traffic. So one such example is if we have a device calling in, say the Nintendo calling in from Zuul, it's going to hit a prod instance. But let's say there's a bug or some other issue that we want to debug. We'll basically set up another cluster or instance that is a debug instance. It's got some sort of special code or debugging that we want to have access to that we don't want to apply to all of production. So we'll create a single instance as an example, and then have Zuul take the same request and in certain scenarios say this specific device or this specific user, route that request to that the debug instance, where the majority of it's going to go to prod. These special cases will get routed to the debug. Another way in which we use Zuul is for squeeze testing. So if we want to check the throughput and make sure that the throughput is not getting compromised, or we want to evaluate what our peak throughput could be for our build, we can basically have general prod traffic go to the prod instance, isolate a single squeeze instance off to the side, and ratchet up from 50 RPS to 60 to 70 and see what the breaking point is. Or if we think that a specific build is flawed, we can compare where that point is. If prod is at 50 and this one's breaking at 40, is it 43, is it 46? Where's the breaking point? How can we learn from that? What kind of code changes do we need to make to the system? So another example where we use Zuul is cross-region failover. So in this scenario, we have US East, US West, where we have prod in both of those. In West, we basically have traffic coming from the western part of the country going to that region, and we have East going to East. If for some reason, and at this point, systems are healthy. If for some reason the East region has a failure and we're not able to really sustain traffic or it's not healthy, we will use Zuul to basically handle requests and route it onto the West region. Now, of course, we need to ramp up capacity on West as well, and so there's a dynamic there. But while we're waiting for DNS to resolve, Zuul is able to control that traffic flow and make sure that we can get the right amount of traffic funneling over and protect us in the eastern region while we're trying to reconcile it. So eventually, DNS will get resolved, and all traffic will then go to the West region. That insulates the East region. We don't have to worry as much about prod and worrying about customers. We can just focus on recovery of whatever's happening on East while West is handling all the traffic. Eventually, DNS will fix the problem, and then we'll set DNS to resolve, and then traffic will continue as normal. So that's one way, or a set of ways in which Zuul can help us. I want to talk a little bit about resiliency. And by the way, Ben, in a little bit, is going to demonstrate a couple of those scenarios in Zuul, and he's also going to demo some of these resiliency techniques as well. So I love this quote from Leslie Lamport, which is, "A distributed system is one in which the failure of a computer you didn't even know exists can bring down your system." This is a snapshot, a portion of the view of our dependency chain. It's quite complicated, it's quite messy, and nobody knows all the nuances in which this can fail. Edge being at the umbrella on the outer edge of the system, we're basically representing this mess, which means that we are prone to failures in ways that we could never imagine. So as the edge and the API, today we're doing about 5 billion requests per second, or per day rather, not second, that's a lot, per day. We have about 30 direct dependent services and many other transitive dependent services. We're slurping in dependent jars from a wide range of sources, about 600 of these. And again, I mentioned about 8-to-1 incoming to outbound ratio of calls, so about 40 billion outbound calls per day. It's a lot of interactions across a lot of different services. One thing is common amongst all of this, and that is that none of these dependent services have an SLA of 100%. So if we were to play this out with 0 at 100%, let's presume that all of these services are at 4 nines of availability. And you cascade that out, it's roughly about 99.7%, which is about 2 hours of downtime a month, which is not great. That's assuming everybody's at 4 nines. If they're really at 3 nines, it's more like 20 hours, and if it's 3.5 nines, it's about 10 hours. None of these scenarios are good. So it's incumbent on us as the edge to make sure that any of these failures, or as many of them as possible, we can mitigate and we can protect against. So if we go back to this diagram, this is the happy path, right? Let's say one of these dependent services fails. Doesn't matter which one, but if that fails, it has the potential, or it used to have the potential, to cascade that up and create a failure across the API layer, which then will cascade all the way up to all the devices, which means that all of you, I presume you're all Netflix subscribers, none of you can stream. Hystrix was our solution to this, right? So we needed a way to get out of the critical path when a service fails. And so we developed this tool called Hystrix. It's open source. If you want to get it, it's on our GitHub site. And coming with that is a corresponding dashboard. And what this is a view into all of our dependent services and the health of each of them, so we have an understanding of how they operate, along with a circuit breaker technology which allows us to toggle on and off our interaction with them. So I'm going to step through that in a minute here. This is a view into just one of those services, and this view is, first and foremost, it's showing a general view into the health of the system. So that green dot is basically the current health, and it's showing you both in terms of size and color how healthy it is. So the bigger the dot, the more traffic it's getting, and if it's green, it's healthy. If it's red, it's unhealthy. And this is refreshing every 10 seconds. The blue line is an ongoing chart of the last 2 minutes, so we can see radical spikes or dips in traffic, so we can understand what's going on over the last 2 minutes. And then all these other numbers and colors basically represent errors, timeouts, other kinds of things that can trigger failure of a service. And all of these culminate into a ratio. And that ratio is basically the error rate. So we're calculating through all of those numbers a percentage of health. And that percentage is tied to a circuit breaker. So if it toggles past a certain percentage and each service has its own percentage, then it will close that, or it'll open that circuit, I mean. An opening of the circuit basically is saying no longer call into that service, call into some fallback mechanism. And there are many ways in which we'll handle the callbacks. We could basically do a fast 500 and just deliver an error. In some cases, like our rating service, which Ben will talk about later, if the rating service is down, the fallback might be, here's an average rating for the title rather than a predicted or your personalized rating for it. So that error rate, when it tips, go to fallback. When it recovers, the service, we ping it every once in a while. When we know the service recovers, then we'll automatically toggle it back on, and everything will flow as normal. So going back to this, if we have that error in that dependent service again, now it looks more like this, and hopefully we can maintain a healthy state. So I want to turn it over to Ben, who's going to talk a bit about both of those and demo Zuul and Hystrix, right?
Okay, that's right. Let me just make sure I'm good here. So like Daniel said, I'm going to show you guys Zuul and Hystrix in action and give you a hands-on view of these technologies. So let's see here.
Oh, yep, sorry.
Switch over here. All right. Is that all right for font size? Can you guys read the text basically? Okay, great. Okay, so the first thing that I'm going to demonstrate here is a technology we have called grepzilla. And you can think of this as real-time distributed tail and grep. And so this is a tool that we use to get insight into traffic flowing into and out of the Zuul layer. And so it gives us a lot of flexibility in terms of like inspecting traffic. So for example, if we wanted to see traffic from PS3s in Mexico where the HTTP status code was a 500, we could use grepzilla to accomplish that. And so what I'm going to do today is I've got our TV UI reference application running on my laptop. So this is basically a tool that we use at Netflix to run the same UI that would run on a smart TV on a laptop. And I'm going to set up tracing for the UI on my laptop. And what I'm going to do is I'm going to do a query by ESN, which is an electronic serial number. This is a unique device identifier. So over here, you can see I've got this simple stream. These are all Python scripts. And so we've got this CLI interface into grepzilla. And this is going to give me Apache access log style output. So I'm going to go ahead and submit that. And so what happens is we have a broker server that my Python program connects to, which then sends that query out to all of our Zool instances. And they're going to start looking for requests that come from a device with this particular ESN. And as they find matches, they're going to start streaming those events down to the broker, which will then aggregate them and stream them down to my terminal so that I can see them. So I've got one up here, and I'm going to run another one, which is just going to give us information about all of the Hystrix commands that are executed for a particular request. And so it'll tell us the names of the commands and whether they were successful or when to fall back, how many times they were executed, the amount of time they took. So now I'm just going to run a quick curl command to the API, and I just want to see that we're actually getting some results here. So there you go. So you can see in the terminal in the back here, 2 lines showed up. And so here we see, timestamp. You see the country from which the request originated, HTTP status code, the Amazon availability zone of the Zool instance that handled the request. This is the EC2 instance ID of the Zool instance that the request hit. From Daniel's pictures, API, we've got a cluster of API servers that sit behind Zool. This instance ID that I've highlighted here is the API instance that handled the request. You've got the environment, so production environment, the ESN from my curl, got a customer ID, response time, and actually let me just pull this over a little bit. I think some stuff is kind of missing here. There we go. So customer ID, response time, and some other stuff. Bouncing down to our Hystrix stream, you can see the request I executed was a search request. You can see there are a bunch of things that also get executed here, but here's the search command. Okay, so I'm going to leave those running in the terminal here, and now I'm going to bounce over to GibbonKit, which is sort of like a specialized build of the WebKit browser that we run on TVs and CE devices. And so this is going to launch our TV UI. So as this thing launches, we should start seeing some events show up in my terminal. And so this is showing you all of the requests that the device is making to bootstrap the user interface. And so if let me just scroll up and we can look at some of these things. So what you notice here is, notice that all of these instance IDs are different. So these requests from my TV UI here, they're hitting different Zool instances, and they're all basically looking to see what queries, trace queries are on the instance, and does this request match? And since the ESN does match, they stream down. So you can see that we've got a bunch of different Zool instances that are handling these requests. Okay, so here's the profile gate. For those of you that are Netflix subscribers, this is probably familiar to you. So I've got a test user, and I'm just going to go ahead and pull up the main interface here. So you can see at the top of the screen we've got our billboard area, and what I'd like you to notice here is this yellow star rating. And so these are ratings. I've actually went in and provided ratings for these titles. And so you can see that, I've done Django and Hunger Games here. I didn't do the Avengers, but let me just go ahead and do the Avengers, and just for the, I probably like it, but let's just say that I don't like it. I'll make it different, hate it. And so what's doing that is, you can see there's a command here called Cinematch get movie ratings. And that's what's actually displaying that star bar that you see in the user interface. And for titles that I haven't rated, I'm just getting sort of a default red star bar. Okay, so that shows you some of the TV UI. You now know where the ratings show up, and you can see how the tracing technology works. Now I'm going to configure some custom routing for this TV UI device. And so I'm going to go over into my browser, and we have a tool here that lets us configure routing by ESN or customer ID or some other request variables. And so I don't have anything set up, so I'm going to click through here. And so what I'm going to do is I'm going to route API traffic. And so I specify an application and then a VIP. This is sort of like an internal host name that we use to route traffic from one service to another. And I set up a cluster just for reInvent. And so I've got an API reInvent cluster running a single server. So I'm going to go ahead and create that. And so let me save that. And so what's happening now is that configuration is getting stored in Cassandra, and all of our Zuul instances are in the background polling for routing changes. And so they're going to find this routing rule that I just added, and they're going to pull it down to their local memory of the instance. And as requests come in from the TV UI running on my laptop, they're going to see there's a routing override. And instead of the request being forwarded to our main API farm, it's going to be, the request will be forwarded to our reInvent instance. And so let me show you guys that. So here, this is a tool called Spinnaker. And this is a sort of a new tool that we're developing to manage our AWS cloud infrastructure. And so this is sort of, will become the kind of base platform for Netflix engineers to manage AWS infrastructure in the cloud. And so you can see I've got this, this reInvent cluster. I've got one auto-scaling group, and I've got a single instance. And so what I want you to look at here is this instance identifier. It's got a lot of C's and a lot of 5s. And so let me go back over to the terminal here and just pop up here and just kind of run a couple of curl commands. And okay, cool. So you can see that rather than being load balanced across a bunch of instances in our main API farm, all of the requests, they're hitting different Zuul instances. You can see these IDs are different. But each Zuul instance knows to route requests from my device to our debug cluster. And the setup that I have on the debug cluster, let me just, I can click over here. So this is pretty cool. This is our base server page. So every app server at Netflix has this page. And so you can see all of the properties on the instance. They're used for the JVM. You can see a bunch of metrics. You can see the jar versions that are on the instance. And so what I did is I went into this one instance and I added a property, Cinematch, get movie ratings. Here we go. And so you can see here I've got this Hystrix property set to force the circuit open. So what that means is whenever that particular API instance in our reInvent cluster, when any code invokes the Cinematch command, rather than trying to go out and get personalized ratings, it's just going to execute the fallback, which is to return just the average rating for the title. So now what I'm going to do is I'm going to just rerun the application. And so you remember we've got the star ratings here. So if I relaunch the app, all of those yellow star ratings should go away. And they should be replaced with the red fallback. So here you go. So you've got red. We did the Avengers, so rather than my one yellow star, we should see the average rating. And if I pull up our Hystrix stream trace here, you can see that the Cinematch get movie ratings command was executed, and it was short-circuited, and the fallback was successful. So you can kind of see how this tracing tool gives you a lot of insight into what's happening with real-time traffic flowing through the system. And the routing tool gives us the ability to kind of shift things around at a very fine-grained level, down to even a single device. So now I'm going to remove the routing rule. So go in here, we'll get rid of it. And again, in the background, our Zool instances are looking for changes to routing rules. They should pick up the fact that this custom routing rule has been removed. And so we should see traffic start to then get load balanced back to our main API farm. And then we should see those, I'll relaunch the app here, the TV UI, and we should see all of the personal user ratings come back. So let's just do a quick test here, and it looks pretty good. All right, so that one did hit the debug instance still. This one hit another instance. Just run that. Okay. So it looks like I think we're good. So I think the routing rule, the removal of that routing view, the removal of the routing rule has been picked up by probably enough of our Zool instances. So let me go ahead and relaunch the TV UI one more time. And we should see the yellow star ratings come back into the UI because we've restored routing to our main API farm. So there you go. So that's all I had to show you guys. I'm going to turn it back over to Daniel to talk about some technology that we use to predictively auto-scale our API.
Cool. Yeah, we're all thrilled that the demo gods were with us on that one. Okay, so now that we're able to control the traffic flow, protect our systems from failures elsewhere, another way in which we can fail is just not having enough capacity or not having the right allocation or provisioning of resources. So what I wanted to talk about now is how we scale our systems. And I love this quote. I think it reflects our mindset on this, which is the possibilities are numerous once we decide to act and not react. And I like to make a distinction between reactive and predictive autoscaling. So reactive autoscaling is the autoscaling that maybe some of you use through Amazon. We use it a lot too. It's still critical to our process, so I don't want to suggest that we're not using it. And basically what reactive autoscaling does is it reacts to real-time conditions, kind of responds to things like load average, RPS, maybe some other metrics, and then based on that, it's going to figure out, are you adding servers, are you removing servers? And it's actually excellent for many scaling scenarios, and it's clearly much better than static cluster sizing. We have found that there are some challenges for us, maybe for others as well. We still use the Amazon autoscaling, of course, but now we've added another component to it to rectify some of these challenges. The challenge is, for example, policies may be inefficient. There are traffic patterns that range from day to day, week to week, and basically we're setting policies that are static across the week or the whatever period of time. So it can be inefficient at times of the day. Performance degradation during instance startup, so you're responding to real-time needs, and then whatever the duration in order to get the instances up is a time that you're vulnerable. So if it takes 15 minutes for a server to be available for traffic, that's a long time. A lot of bad things can happen. Outages can trigger downscales. So basically, if you are experiencing an outage and an origin server is not seeing the traffic because, well, Zool is doing something else with it, then you might downscale the size of the API backend, in which case, when it recovers, you could be in for a world of hurt. And then you're ultimately at times going to be in excess capacity at various times of the day. So in response to some of these challenges, we created a system called Scryer, which is a predictive auto-scaling engine. And I'm going to talk a bit about how it works and how it's effective. So the way it came to be is we looked at these patterns and said, you know what, this is pretty consistent on a week-over-week basis. We as humans can see this. So if we as humans can see it, probably a computer can see it too if we make the computer smart enough. So that's what we did. We set out to say, you know, let's build an algorithm that will evaluate those patterns and predict what the next moment is going to look like. And this is ultimately where we arrived. So the blue line is actual traffic, and then we started developing the algorithm, and I think the predicted looks pretty good. So based on that, and just kind of scouting out what that will look like, we started to experiment with actually toggling the scaling events. So we took predicted workload for a given day, and then we started to modify the scaling and started to step up the scaling, step down based on the predictions, and that started to look really good too. And so now actually many of our systems are operating on Scryer. So what's it doing? It's evaluating historical data week over week, day over day, month over month. I don't think we're doing much year over year, but we're taking these metrics and using that to prompt what do we think the next one's going to look like. And when we're scaling, we're really just adjusting the minimums. So we're saying we're expecting that at this time, no fewer than this number of servers is needed. And then we're relying on reactive auto-scaling to handle anything above that we didn't anticipate. So the results of Scryer, quite favorable. If you look at load average, we saw a lot spikier load average with reactive auto-scaling only. With the two of them working in concert with each other, we're seeing a lot thinner range between the spikes and the troughs of load average. And that actually translates pretty well to response latencies. So if load average is less spiky, then boxes are healthier and able to respond more appropriately or more timely to requests. And so what we're seeing here is our response times are much better or much more consistent. Talked a bit about the outage recovery. And this is actually a big deal for us because what used to happen for us, or generally the pattern that we would see around outages is something would happen, we would start plummeting in terms of our traffic, we would eventually recover, and then we'd get a retry storm or a request thundering herd storm back into the system, and we were under-provisioned for that. And the under-provisioning actually extended our outages for some period of time. So it might actually double the duration of the outage. What's happening here, though, with Scryer is that we're maintaining that minimum instance count based on the prediction. So even if it drops down due to an outage, when it recovers, we're correctly provisioned for what the traffic should actually look like. So we're actually cutting off that secondary part of the outage. And then, of course, AWS costs, because we are much tighter in our provisioning needs and we're not dealing with those inefficiencies of the varying traffic patterns, we're able to keep the costs a little tighter, which is good for us anyway. So key takeaways from everything that we're talking about here. One, routing is important. And I would emphasize that not only is routing important, but it's key to separate out the routing function from the processing function. And that's what we've done. We've had Zuul do the routing, hands off to an origin server, some cases API, playback, website, wherever it's going to go. And that allows the website to be protected from other issues by Zuul. So that's quite important. Resiliency is also important. So can we prevent our systems from failing? Can we prevent or protect the customers from the failures of others? Another key component to this is drift is going to happen. Systems are constantly getting more and more complicated. They're evolving. New things are happening. And like that Leslie Lamport quote says, more things are that we don't even know exist are able to take down our system. So it's important for us to constantly be evaluating this and modifying the Hystrix configurations, checking out timeouts and retries and things like that to make sure that we're not going to end up in this scenario where we don't know that something can take us out. And fallbacks is a key component to this. If we can actually do something like the ratings, the Cinematch scenario, and offer some other less optimal output, that is, that's a great way to go. Scaling is important, and I believe pretty wholeheartedly that being proactive on your scaling needs, both in terms of capacity planning or using something like Scryer, rather than just reacting, is optimal. And finally, open source. We take from the community, we give back to the community. We talked about Hystrix and Zool and Scryer. Hystrix and Zool are open sourced. Scryer maybe someday, but they're out there, along with, I don't know, what's our count? 50, 60 projects out there on the GitHub site, so if you want to check those out. Again, I mentioned Sharma's talk on Friday, so if you want to check that out. And then we also had a range of other speakers. I think we're going to have a range of office hours tomorrow and Friday, so if you want to come talk to us about any of these sessions or check out the slides, they're all there. Ben and I will be at our booth in the expo hall at between 1 and 3 tomorrow, so if you want to come talk to us about any of that. And those are our slides. So, questions? Any questions? Did you hear?
Yeah, the question was, if ELBs supported all of the routing functionality that we wanted, would we use Zool? I'm not really sure. Probably not, but they don't, and they probably wouldn't support the same level of programmability, programming support that we would want. So, I think if anything, we might actually move away from ELBs and just have Zool be the actual entry point for all of our traffic.
How do you guys use Zool for intrusion monitoring and data protection?
What was the question again?
For what?
How do you guys use Zool for things like intrusion monitoring and data protection or data?
Right. So yeah, the question is, how do we use Zool for like intrusion detection and security? And so Zool, different origin applications have different requirements, and we do have, like our website team has some code that they write for Zool that, does some of those things, and they have their own kind of custom code that does, rate limiting, for example, if you see too much traffic from like a particular IP address or something like that.
So you do that on Zool, but different people program different. Does it sound like different teams program differently for it and put it into the configuration? Or?
Yeah, that's right. So we have a security team who specializes in figuring out where the intrusions are likely to happen or what's actually happening, and then we expose mechanisms for them to inject in what they want to have happen, and that all happens at the Zool layer.
On the grepzilla stuff that you showed, how are you getting it looked like you were showing like the classes that were being used through the request in your Java application. Yep. So how are you pulling that data out? Are you running like sidecar agents on your application servers, or are you querying them directly through JMX ports or something along those lines to get that data?
No, it's actually, it's simpler than any of those things. Basically, when an API server gets a request, we just track the Hystrix commands that execute in the context of that request, and it just gets stored in memory for that particular request. And then there's a filter that basically writes all that stuff into a response header that gets sent back to Zool, and Zool can then just stream that down.
Maybe I'm missing something, but in an earlier slide you mentioned using Zool to redirect traffic to another region that was having an outage. Yep. How do you do that if the region's having an outage?
Yeah, good observation. If the outage is like affecting Zool, then we can't. and you just have to move DNS.
Yeah, it depends on the nature of the outage. So in this example that I showed, it was a Netflix service problem, maybe a deployment or a bug, not an AWS regional outage or anything like that.
But it's also worth pointing out that the region that you're failing into, even if you need to just kind of update DNS and you can't have one Zuul, cross-region proxy to another one, that Zuul in the region where all the large influx of traffic is coming into it, we throttle there, and we gradually kind of let traffic come in as the back end starts scaling up. So it plays a role in the failover process, regardless of whether or not you're cross-region proxying from a failed region.
No, wait, Mike, right there.
Can you speak to more, I guess I come from more of a traditional website background. Can you speak to resiliency on the website part of your service?
Okay, so for us, website is basically, we're in a hybrid state right now, right? So historically, there is a legacy component to the website. We're moving on to basically fitting on top of the model that I described today, in which case the website is just another presentation layer. So that is where we're moving to, and we're partway through that. Historically, though, the website basically had its own infrastructure layer underneath that, and they were using similar techniques. So they had their own cluster for Zuul. They incorporated Hystrix for all their dependency calls. It was basically the same pattern. It's just separated out. We're now consolidating that into one pattern and one flow.
Since you do so much testing in production, I guess, how do you manage it with the developers? Like, does a developer have the ability to route a particular traffic for a particular device to a new place and then forget about it or something like that?
Yeah, so that tool that I was showing you guys where I did the routing by ESN, by default, those routing rules have a TTL, and so they expire after 30 minutes. So if you want it to last around longer, you have to just increase the TTL.
Everyone does have the ability and the right to go and do those things, and we just trust that people will do the right thing.
Yeah.
Oh, yeah.
Yeah, simple question. What's the ratio for Zuul instances to API instances?
We don't have nearly as many Zuul instances. Like Daniel mentioned, one request into Zuul is one request out. And at the API tier, that's where all the work is happening. So I don't know what the ratio is off the top of my head, but it's half as many instances, maybe fewer.
And it's not even always one incoming Zuul goes to an origin either. So there could be fast 500s or something like that. So any number of things can happen.
Do you guys use a CD? I know you guys have your own OpenConnect. I guess you guys probably don't use CloudFront to serve up static assets beyond just media, and how does that work with routing with Zuul? Is it just a different domain name, something like that? How does that work?
Yeah, so we don't like all of the UI assets. They're hosted on a CDN, and we don't use Zuul for any of those things. So yeah, it just really depends. Most of our non-streaming functionality is, basically all of our AWS functionality is fronted by Zuul. And a lot of the kind of Chrome assets in our UIs and like JavaScript, that's all CDN hosted and not controlled via Zuul. Yep.
Okay, last question. Where was it?
So when a new instance comes up, presumably it has to let Zuul know of its existence. Does that happen through Zookeeper or something like that, or does it just notify an API endpoint that, hey, I'm alive, and then now the routing rules apply to me?
Yeah, so Zuul uses Eureka, like everything else at Netflix. And so, yeah, we just have it configured by like a VIP address for like our API farm, and as Zuul instances come up, they know the VIPs that they're routing to, and it's all, we're using the same stuff that's open sourced.
Cool, so we have to wrap up the room here. If you want to talk to us, we'll be around here for a little while, but we'll also be at office hours at our booth 1 to 3. Yeah. Thanks a lot for coming.